Okay, so today we will talk about crystal defects. Crystal defects. Okay, now when we talk about crystal defects, now what are defects of crystal defects? What are crystal defects? It is actually of crystal, departure of crystal from its perfect regularity. Crystal structure from their perfect regularity. We have already told that crystals have a very regular structure, with in the case of ionic crystals, you know that they have cations and anions. They are perfectly fit into the crystal lattice, with each anion being surrounded by cations in a proper fashion, so that the crystals are electrically neutral. Okay, any deviation from this perfectness is what is called a crystal defect. Now, these irregularities or defects, these irregularities or defects will affect the affect the crystal in its many properties. That is, the properties which are affected, properties which are affected by this irregularity, which are affected are electrical property. What is meant by electrical property? Ability to conduct electricity. Electrical property. Then mechanical property. Mechanical property, that is ability of the crystal to bear stress, or okay, the ability to bear the stress. The strength of the crystal will be differing, and also optical property. This is one of the important properties of crystal molecules, crystalline compounds. Optical property, that is optical properties may include diffraction, deflection, reflection, and all these stuff. Okay, so all these will be affected by the crystal defect. Now let us see what are the different types of crystal defects. Number one, we have three types. You can classify them. Crystal defects can be classified into three types. You have point defects. Second is line defect. And third one is plane defect. Okay, so these are the three types of defects, and the name itself will tell you what it is. You can just conclude that these are related with the say for example, the point defect will be related with the defects in the lattice points. Line defect will be the defect in the whole line of cations or anions, which are arranged, and also the plane defect will be related with the change in the plane, or maybe some of the planes are closer, some of the planes are farther away. All this depends. Now we will be dealing only with the point defects. Okay, we'll be discussing only the point defects over here. Now the point defects can occur. Point defects can occur due to the different factors. Number one, vacancy in the lattice site. Vacancy in the lattice site. That is first one. Second, shifting to interstitial positions. Shifting to interstitial position. Shifting of the anions or cations to interstitial positions. You know what is interstitial position? That is, you have a regular arrangement of the atoms or ions. These are the regular arrangement of atoms and ions. Some of the atoms are moving into this place. See here. So that is what is meant by shifting in the interstitial position. Okay. The third will be due to the presence of interstitial or substitutional impurities. Presence of interstitial or substitutional impurities. Substitutional impurities. And the fourth one, this is presence of impurity coming from outside. Okay, or this can be deliberately put into it to change the properties. You can deliberately put them into it to change the properties. Okay, so okay, so that is now substitution. Now interstitial means you are putting the impurity in the interstitial position. Substitution impurity means the impurity which you are adding is removing one of the atoms or ion from the lattice point, from one of the lattice point, and it will occupy there. Okay. The next we have non-stoichiometric impurities. Non-stoichiometric. That is, the stoichiometry is changed. By the addition of impurity, the stoichiometry is changed. So let us see one by one What are the different types of the crystal defects, and find out. Now stoichiometric, we have two types of point defects. You can classify the point defects as stoichiometric. Point defects are one, stoichiometric. Stoichiometric means you are not changing the overall stoichiometry of the crystal. That is, the formula will remain the same. Say, for example, if you have NaCl, it will remain altogether. It will remain NaCl itself. Number of cation will be equal to number of anion. That is the meaning of stoichiometric. Okay, so the material remain unaltered. Only position will change. Material remain unaltered. So where does the change occur? The change occurs, okay, in the position. Now this can be intrinsic type or extrinsic type. Now intrinsic defects means the defect occur from the atoms and ions within the crystal. Okay, intrinsic defect. Intrinsic defects arise from atoms or ions within the crystal. Within the crystal. This is called intrinsic defect. Now, the stoichiometric defect, we have two types. One is schotsky defect. Two types of stoichiometric defects. There are two types of stoichiometric defect. One is schotsky defect. Okay, this is the most common defect which is observed in many crystals. Okay, where an ion or atom is missing. That is what how you can describe. An ion or atom is missing from the crystal lattice. Is missing from the crystal lattice. Okay. Now, this occurs generally in ionic crystals. Generally, this occur in ionic crystals. Okay. Now, okay. So, we have the ions, an ion is or atom is missing. Now, this will occur in ionic crystals. Occur in ionic crystals. And remember, there is no change in the electrical neutrality. That is, the electrical neutrality will not be changed. Electrical, that means it will not conduct electricity. Rather, we should say overall electrical neutrality, the total plus and minus will remain the same. That is how we can put it better. The electrical neutrality will not change. Because conducting of electricity is not directly related with this, okay, that we'll explain later when we come across the property of these crystals. So now let us see how does this defect look like. See, I will draw the molecules or the motifs here. Suppose this is an NaCl crystal. Okay, now NaCl will have one, see this, these are the NaCl, Na and Cl crystals. Crystal lattice. And you know, this is we can consider only one plane. This is, you have to remember, this is three-dimensional. Okay. Now you have Na, the positive Na, then the negative chlorine, positive Na, negative chlorine, positive, negative, and then you have positive, negative. Now one Na is missing here. This is missing. Okay. Then you have a chlorine here, Na here, chlorine here, Na here, and now see correspondingly one chloride also is missing. And that is what I told you, the electrical neutrality, negative, positive, negative, positive, and negative. That is what is told. The electrical neutrality will be maintained. That is, one anion is missing, cation is also missing. You have to remember that. Anion as well as cation is also missing. That is how you maintain the electrical neutrality. So this is how it will look like in the crystal structure. You have two places where the two atoms are missing. Now suppose you have too many of these missing atoms in a crystal. Whatever is the number of missing molecules, the electrical neutrality will remain the same. Okay. And but the stoichiometry is not affected. Stoichiometry is not affected because for each sodium, one chloride will be lost. So, stoichiometry remains the same. Electrical neutrality also remains same, right? In the case of NaCl, one sodium is lost, one chloride is lost. In the case of MgCl2, that you remember, three sites will be one site of Mg and two sites of chloride will be lost because for each Mg you have two chloride. Now, if you have too many of these, too many molecules lost from this type of defect, then you will have too many vacancies. That will cause too many vacancies here. That means vacancy means the atoms are lost, and that will reduce Two large defects, two large defects will cause lowering of density, will cause lowering of density. The material will become less dense. Okay. Now they will, these, I told you just now, I was telling you about neutrality. Electrically they are neutral. But due to the presence of these positive and negative uh, missing sites, okay, there will locally there will be a small development of a charge locally. Okay, what happens is, and due to this development of charge difference, the neighboring ions will migrate to the vacant position. Neighboring ions neighboring ions may migrate to the vacant position. And what will happen? The that place where the neighboring ions were there, that will become vacant. Say, for example, from here, one atom is migrating from here to here. This place will become vacant. And this is getting transferred. So another one will come from here to here. And this phenomenon will get transferred. Okay. And this polarization, say this is the anion, right? So the vacancy arises on this side with lack of negative charge. So there is a small increase in positive on this side and negative on this side. Okay, so this will cause a little bit of electricity, migration of electricity. Okay. Now, I told you the most common type. The most common crystals are sodium chloride, potassium chloride, bromide, potassium chloride, cesium chloride, etc. These are the more common substances which causes this defect. The second one is Frenkel defect. Frenkel defect. Here what happens is atoms will move into interstitial positions. Atoms or ions shift from lattice points. Shift from lattice sites or from the lattice points to interstitial positions. Interstitial positions. This is what is called Frenkel defect. Okay. And again, think about a cubic structure. I think about a simple cubic structure. If you consider a simple cubic structure where simple cubic, you know, it can have motifs only in the corner, right? Only in the corner you will have the motifs. But suppose one of the motif is missing from one of the corners, And what you get is, you get, see, you have motifs of all the coordinates. You have the motifs on all the coordinates. Okay, maybe one of them is missing. Say, for example, here it is missing. And that atom is coming and occupying the central portion. In between the planes. That is what you call as interstitial plane. Okay. So cations are displaced. So cations are getting displaced. Cations can generally get displaced. Into interstitial position. Interstitial positions. Now this occurs because normally if you consider an atom consider an atom like silver bromide, AgBr. This is observed in silver bromide. Now silver compared to bromine is small. Cation is small cation. Small cation and large anion. Small cation and large anion. And this large anion, when you have large anion and small cation, the cation can be displaced and go into the interstitial position. So here the cation is displaced and move to interstitial position. Okay, so this is what is a Frankel defect, and the examples, as I told you, you can see the salts which have got small cations and large anions. Such compounds will be showing these defects, and other examples are silver iodide. You can see iodine is still larger, and then you have zinc sulfide. Sulfur is quite large. Okay, so these are the cationic defects. Then there are Frankel defects in due to anions. That is displacement of anions. Like you can see here, calcium fluoride, CaF2, strontium fluoride. Again, you can see here the anions are not very large. Anions are smaller. Strontium fluoride, Sr, strontium fluoride, and lead fluoride. Again, you can notice these are observed in fluoride compounds. This anion Frankel defect. They show anion Frankel defect, meaning anion Frankel defect, meaning anions are displaced. Anions are displaced into interstitial position. Interstitial position. Okay. So the other types we'll discuss next time. Okay. Thank you for your cooperation.